Okay, so we have a couple of actual Physics 2 questions here, which hopefully you notice some of the differences that you have to do a little bit more writing about the whys and a little bit less pure calculation. So this one's going to be a little bit harder for me to do on this. It's going to be a lot more talking and a lot less writing because of that. I'm not going to write out what you would want to write in the page. I'm just going to talk about it. So first, we have an ideal gas process. We have 3 points labeled A, B, and C. We're told we have 2 moles of a gas, that it's an ideal gas, and we're told the cross-sectional area of the piston. So our first step in part A is to calculate the force that the gas exerts on the piston while it's in state A. And so to do this, we have to remember there's a relationship between pressure and force. The definition of pressure is a force divided by an area. And so what's really happening, right, the picture of what this system is that we have like a bucket with a piston kind of like that. Right, this is our piston that can move up and down, kind of like that. And the gas is all in here bouncing around, and it exerts a force upward on that piston that opposes gravity. That would, without the gas inside, the piston would just fall. Right. So the area that matters is that area of the piston which we have, and we know the pressure at state A. That's from the graph. So the force is the pressure times the area. At state A, and this is where reading the axes is important, right? This is in units of 10 to the 5th pascals. So the pressure at state A is not 1.0 pascals, but 1.0 times 10 to the 5th pascals. And the area is 5 times 10 to the negative 3 square meters. So you multiply those out, and you're going to get 5 times 10 squared newtons. Right, that's a force. And that's A part 1, well, the mathematical part. So the next step is the explanation part, right? So why do the collisions cause the gas or allow the gas to exert a force? And there's a couple pieces to this. The first is recognizing, this is a physics 1 type concept, right? Is that in a collision, the gas particles are going to be, right, if this is our piston top, the gas particles are going to go kind of like that. They're going to come in and then bounce off. And so this means that the gas particles change momentum, right? Their velocity direction changes. It's essentially an elastic collision. So because we have an elastic collision, the gas particles' momentum changes. Therefore, because of Newton's second law, the piston must exert a force on the gas particles, right? That's the only way the momentum of the gas particles can change. And then, since the piston exerts a force on the gas, by Newton's third law, the gas must correspondingly exert a force on the piston. And so referencing the fact that both Newton's second and third law are required, and as well recognizing that like change in momentum requires a force, is what you need to get the part 2 points. So that's part A. Well, A part 1. It's 2 parts, even though it's sub part. Anyway, so A part 2, calculate the temperature in state B. Well, this is going to be an ideal gas law, right? We know the pressure and the volume, and we know the number of moles, and we know the gas constant. So we're going to use PV equals nRT. We'll rearrange. Right, and since we have a number of moles, we're going to use the gas constant R as it appears on the AP sheet. So the pressure in state B, right, 10 to the 5th. The volume of the gas in state B is 0.10 meters cubed, 2 moles, and the value of the gas constant is that 8.31. And then that thing has messy units, so whoever needs to cancel stuff. And so if you calculate this out, you get 602 Kelvin. Right? So that's the simple calculations part, is just applying the ideal gas law. You know enough information to solve for the one unknown of temperature. So now we need to indicate the microscopic property of the gas that's characterized by temperature. And there's an equation that will help with this. But we can't just reference the equation. We have to talk about it a bit more. So we have the definition that the internal energy of the gas is 3/2 N kBT. And the internal energy of the gas is the random molecular motion, right? This right here is an average kinetic energy, right? Actually, I should rephrase that. This isn't the average. This is a total kinetic energy of all the particles. So the microscopic property of the gas, right, is I'm going to write it as little u to make it little u is just 3/2 kBT, where this is now the average K of one molecule, right? And so this is what they mean by the microscopic property. The temperature tells you sort of the average kinetic energy of one. You notice the only thing that's different here, right? I didn't write this is the total number of atoms, and it's not present in that one. So what they were looking for is that it's the average kinetic energy of a molecule of that gas. Okay, part B. Now that we've done sort of the descriptive part, so we now need to predict how the internal energy changes when we go from A to B, and then justify it. So we can reference equations, but we aren't expected to just do a calculation. There's a couple different ways you can do this. The easiest one that I think of is we know that the internal energy, that's that U, is related to the temperature, right? If the temperature goes up, the internal energy goes up. If the temperature goes down, the internal energy goes down. And so we can figure out how the temperature changes from A to B. We can figure out how the internal energy changes. And I think it's kind of clear from inspection. Remember, isotherms on PV diagrams look kind of like this, where T1 is always less than T2 is less than T3. And so because of that, we can tell that TA must be less than TB. Therefore, the internal energy must go up. That would be how I would justify it. I'd say that the temperature at B must be higher than the temperature of A because it's on a higher isotherm, and we know the internal energy is proportional to the temperature, so the temperature must go up. Another thing you can do is you can note that the gas going from state A to state B expands at constant pressure. The only way for it to expand while keeping the pressure constant is if the temperature goes up, right? That makes all the collisions more powerful. That's how it's able to expand, because the molecules are traveling faster. So if you do reference something like that its volume increases at constant pressure, the only way for that to happen from the ideal gas law, right? If this goes up, then the only thing that can happen to T, if everything else is constant, it must go up as well. That's another way you can get at it. And again, you don't have to do a calculation, you have to just kind of reference some of that general stuff. Part 2, we actually need to do a little bit of a calculation. We want to figure out the energy added to the gas by heating. And that's an important word, right? We don't care just about the change in internal energy. We care about specifically the energy that's added by heating. And so this is where we have to reference that first law of thermodynamics, which is delta U is Q added plus work on, right? And these are all things that we can calculate sort of piece by piece. So this, we've kind of used this equation a couple times. This is 3/2 total number of molecules KB delta T. Oops, that should be a capital T for temperature. This is negative area under curve. Right? That's something we can calculate from the graph, and it's actually very easy. It's just a rectangle, right? So this is negative P delta V. And so if we can figure out those things, right, this is TC minus TA, right? Final minus initial. This is VB minus VA. And the reason I write volume of B is that, right, going from B to C has no work done because there's no area under the curve. Right? So we can just calculate all these little pieces, we can solve it. So this one, the work is easy. Right? The pressure is a constant 1 times 10 to the 5th pascals. VB minus VA is 0.06 meters cubed. So this works out to be negative 6,000 joules. Now we need to calculate temperatures of A and C, right? Actually, let's give myself a little bit more space here. Right, if we knew TA and C, then we could do this pretty easily. We're just going to use the ideal gas law, kind of like we did in the second part of part A. So PA VA over NR. And we know those numbers, right, reading the pressure and volumes off the graph. This is 241 Kelvin. And similarly for the graph in part C, we get 301 Kelvin. So we have, right, so this little bit right here is 60 Kelvin. So now we just need to figure out how many molecules we have, right? This capital N is the number of molecules. We know the number of moles, so we need Avogadro's number. So this is 3/2 times the number of moles times Avogadro's number times KB times 60. That's the delta T. And those are all numbers that we have. You need to plug them into your calculator carefully, but if you do that, you get 1,500 joules. So now we're ready to actually substitute everything in, right? We get, in the end, 1,500 equals Q minus 6,000. And so we can just solve for Q quite easily. Right, 7,500 joules. And that must be the amount of heat added. And it makes sense that it's a relatively large number, right? Going from A to C, the gas must do work, so it has to lose energy. That's the negative 6,000 joules. But the temperature on the whole goes up, so it has to gain more heat than it loses in terms of work done for the energy to all sort of balance itself out. All right. So part C, you gotta do a lot of math, or you can do it really, really quickly. So the change in the total kinetic energy, right, that's the internal energy. Internal energy and total kinetic energy are the same thing. So delta U, and I'm going to write this as CA, can be written in a couple, well actually I'm going to start a couple things. So we want to figure out the change in total internal energy as we go from C to A. And we just did, right, we just calculated delta U from A to B to C, and we care about what's delta U from C to A. Well, the sum of all of those is the same thing as delta U A, B, C, A, right? That's a complete cycle. We went from A to B to C and then back to A. So since the internal energy depends only on the temperature, this must equal 0. Like the temperature at point A is the same. If you end up where you started, your change in temperature is 0, so delta U is 0. This we got before. This is 1,500 joules. And this last bit, is what we want to find. And that's a very easy equation to solve. Right? And so when you do that, right, it's just x equals negative 1,500 joules. Right? And that's the answer. You also could come at this, right, a different way. Delta U Ca is the work on gas as you go from C to A plus Q. Actually, I'm not sure if you can do it that way. I don't think you can, now that I think about it, where you don't know enough to solve it any other way, because you don't know the heat. You could calculate this. It would be a pain. But without the heat, it's kind of meaningless. I think that's the only way you can get it is this little piece right up here. So I'm going to cross that one out. And so it's really important to note there's a lot of talking that I did, right? All those things that I said more or less have to be written somewhere. Part A especially, but you have to explain how you're arriving at some of these results that I talked through but didn't always write down. And that's really the differentiating factor between a Physics 2 question and an old Physics B question, is that level of explanation they expect of you. So make sure that as you're kind of checking these, that you're also being comfortable with all the stuff I explained, not just the stuff that's on the screen written down.